I'm going to kind of shift you immediately to the work we're doing at the University of Bristol. So what I'll present is work we have conducted in the lab in the past 3 years. Please stop me. I believe you're going to see a bit of a gap. We're going to have some new things like a series network or 3D convolutions without explaining them in sufficient details. So stop me if things get out of track. But the talk is about a fine-grained perspective onto interactions with objects. And the images you see are images captured from what we call an egocentric perspective. So a wearable camera that could be on your glasses or head-mounted, observing what you do as you move around the world. There is increased interest in computer vision and machine learning in thinking beyond labeled data. The logic is, we as humans, we don't start with 1,000 labeled data of what a computer is before we learn what a computer is about. We move, and as part of our movements, we learn. And we do have an egocentric view of the world. We hold our eyes, they're not looking at us, they're looking at the world as we move around. Egocentric perspective comes from the word ego, which is the person's belief in their self-esteem or self-importance. And egocentric vision is this understanding of the world from the wearer's perspective. So someone is holding the camera, and the intention is to understand what they are doing, what objects they're interacting with, what people they're interacting with, and what's their intentions. The typical application is towards giving them guidance or directions, human-computer interaction. However, in computer vision, we're first solving the perception problem. Can I know what this person is currently doing? And let's start by some videos of what an egocentric view would look like. On the top left, you're seeing social interactions from a dataset from Georgia Tech. Top right and bottom left are datasets we have at the University of Bristol, which I'll tell you more about, that object interactions indoors, in the kitchen and in the gym. And bottom right is a dataset from CMU, from Carnegie Mellon University, that focuses on sports outdoors, again from an egocentric perspective. It might cause a bit of dizziness looking at this footage, because you are stationary, but realistically that is how we see the world. And even though we usually call it first-person vision or egocentric vision, this might not necessarily be a person. And this is some of the footage from the BBC documentaries where the cameras are mounted on animals, in this case a bird, and you can figure out what this one is doing. This is going underwater, getting a fish, sharing the fish, and then going for a swim. And there is currently lots of footage on other types of intelligent agents from a first perspective. Right, so what can we know from a camera that the person is wearing? One of the things that typically you find lots of applications and potential in is navigation. If I know where you are, I can give you directions of how to get somewhere. And you've probably seen lots of footage of saying, take left or take right, whether it is a car or a human. I'm not going to talk about navigation, it's a big topic. And then the second popular thing when you talk about wearable cameras is augmented reality. These goggles, and then you have something projected onto the world, like a Pokemon, and then you're running after it and doing some sort of game. The topic that's less talked about, but gaining lots of interest, is called diminished reality. So this is not adding something into the world, this is removing something from the world. And let's see some data.
In this video, we describe a dip painting method for removing dynamic objects that include static scene backgrounds. Our method was used as input for the video.
So again, you have the foreground, you have the background, you're focusing on the things you want to remove, and this disappears.
Objects, we first align frames to each other.
And this is really interesting, this concept of removing, of diminished reality. I'll show you another example of diminished reality, again from a wearable perspective. So you can focus on, you can track the world, know where you are relative to the scene. Then you can highlight the object you want to disappear, and you can in-paint it. This is not very recent, this is 2016, so there's even more recent things about diminished reality. So you can think about a world where you can wear goggles, then you can highlight the person you dislike in your office, and they just disappear. Forever, you don't see them. Right. Again, most of the work you see in egocentric or wearable vision focuses on navigation, augmented reality, or diminished reality. The work we do in the lab focuses on what you're doing and how well are you doing it. So at the University of Bristol, our topic is a fine grained, a detailed understanding of people interacting with objects from a wearable camera. This seems so detailed, but that's what research groups are about. You have one topic, and all of you are focusing on kind of advancing the state of art on it. And I'll start by showing you an example. Imagine how many questions you as a human are answering about this video. This video has so much in it, it's even difficult to count the number of questions you're going to put. You're going to say what objects the person is using, what they are really doing with those objects. They are kind of doing multiple interactions. Then they have a certain goal, which certainly they have not completed. And then you can think, what could be the next action? Each of these is a machine learning question that could be addressed as part of a specific project. Why are we interested in this? I'll start by telling you about the initial project that initiated our group, which is called You Do I Learn. Then I'll focus on some research problems we've solved recently. One is talking about skill determination, how well are you doing something. One is about focusing on the completion of actions. And finally, I'll tell you about the data set we've collected, because anything to do with machine learning has to collect natural data set. And last year we released the Epic Pictures data set, which is the largest data set in first-person object interactions. Well, I'll start by the potential or the applications. There are lots of objects in the world that you might not know how to use. You arrive to Morocco, to the airport, and you have this ticket machine. Right? We're still social human beings, so you might turn around and ask someone, how do I use it? But increasingly, particularly in the West, no one asks one another, they ask Google. Therefore, how do I use this? How do I get from something to another? Usually this is done because there are people really, really nice who upload instructional videos to YouTube, add text to them, how to buy a ticket in Casablanca airport. You can then use the text to search for this video, you watch it, and you can then use it. Similarly, you might get home, you've bought a new device, it doesn't look intuitive, you want to figure it, so you ask YouTube. But what you're querying is the text that someone has used alongside the video. The mission of this project was to try to look at a wearable camera of someone doing the action, and then a wearable camera of someone attempting the action, and then feed the information from the teacher to the student without any text involved, what we refer to as unsupervised. So there's something in the footage that tells us that this person knows how to do something. We capture the footage, we feed it to someone who doesn't know as a video, no text is involved. The potential for this type of You Do I Learn interaction is huge. In 2016, we produced one of the first prototypes for this, and this is an offline prototype. What you see in the middle is a cross that represents the gaze of the person, where the person is looking. We get gaze by wearable gaze trackers. These are two cameras that you put on your glasses. One camera looking at the scene, the other camera looking at your pupil, which is actually observing how you're moving your eye. We go through a step called the calibration state. So you basically ask someone to look around, so you calibrate where in the image they're looking. And after that, they can go around the world, and you can have this yellow cross of where they're currently looking. And humans go through lots of steps in how they do interactions. They first fixate, they first look, and then you act. So particularly from a wearable perspective, gaze is very important. What you'll see is I'm going to freeze the video, and you're going to see a suggestion from someone else about what you could do at this step. And that's why it's called an offline demonstrator. So a person is looking, and this is a suggestion from someone else using the same object. Again, fully unsupervised. There's no text involved. Some of these are meaningful, some are less meaningful, but again, you're looking at the object, given the current state of the object, you're providing a suggestion. We don't know that this is called a screwdriver or that this is a socket. And again, you're providing a suggestion from observing the world by someone who knows how to use it. After we produced this demonstrator, we actually coded all of this onto Google Glass. Google Glass was this Android device that came into being, this camera that's looking at the world and a small screen that gives you evidence. We were very excited because it was one of the first wearable computers. It faced lots of criticism on privacy, if you've heard about that. I'll discuss privacy with wearables towards the very end, but here we're focusing on the algorithm. Again, what we're doing is this you do, I learn concept. There is a person wearing the wearable tracker. It has an estimation of their gaze. They're going around looking at objects and using them. What we're capturing is the appearance of those objects, as well as the act they're performing to operate those objects. We're getting a tool in our lab. We have this, what looks like a car out of some autonomous driving project, but they're just going around the world, using objects in the world. He walks out, he uses a ticket machine. The system is automatically doing two steps. One, figuring out what objects and how they have used them. By the end of the process, the system has captured the various interactions and captured these short video guides of how these objects have been used. So that's 1, 2, 3, 4. These are kind of simple interactions. But you kind of know how to use these objects. Everything is done automatically. We don't even know the number of objects that the person is going to interact with. And then comes the learning exercise. So what Theo, who's also a professor at the University of Bristol, is using the system. So he's looking at the object. What he's doing is he's looking at the object and he is pausing. So the system is reading his cue as uncertainty and is giving him in this small video a guide or a short clip that has been captured by the expert of how to use that object. If you're interested in you do I learn, you're going to see lots of videos we've done, also on things that might not be trivial, like using a sewing machine, but the concept called you do I learn. How can we bridge the knowledge of using objects in the world to teach someone else without the intermediary supervision of text? You do I learn was like a fundamental concept from which lots of research questions emerged. One question was, if I see 10 people using the ticket machine, who is the person to learn from? Because there might be 9 who actually have no clue what they're doing. That might not be the ones I want to use to teach someone new. How well is the person doing something was one of the questions we raised. Then is, when are they doing it? Plus, can we use other types of modalities like audio, etc.? So I'll take you through the cycle, but I started with the potential or with the application. It's called You Do I Learn. And the first step is talking about skill determination. Right. Imagine you see 8 different people doing a fundamental task like rolling a pizza dough. How do I know who is the expert? I do want to learn from the expert. There's no point in learning from someone who really doesn't know what they're doing. And because we are talking about daily tasks like pizza, we don't want to create an Olympic system to give them marks and say this pizza is 7 out of 10 rolling. What we want is just to get a relative rank. To say this person is doing it certainly better than the other. So this is just a relative rank. There's lots of research in skill determination that's focused on types of applications like the Olympics, where the output is a score, or on surgery, where the output is a score. There's lots of things in the world where we don't want to score them, but we still can, or want to figure out if someone is doing it any better. And like all research in machine learning, you start first supervised. So you start with annotations to figure out whether you can even do this problem. And the annotations in this case was pairwise annotations. So people were shown 2 videos, of, let's say in this case, drawing, and we as humans, we can assess who's actually a better drawer. So we're looking at the video, and the objective of a human annotator, this is collecting labels, is to say which one they believe is doing it better. They will watch the video, and somehow towards the end, lots of people will agree that, this person is certainly a better copier or drawer. The same type of annotations could be collected for other tasks. So again, you can see people rolling a pizza out of a pizza dough. This is shocking, but apparently this is what they do in the US. They have like a roll where the pizza is inside and they get it out of it. This is a data set collected at CMU, and we have relabeled it for skill. Which person is doing it right? Towards the very end, they both succeed. In the drawing task, you might say towards the end, I know who's better for sure. But in the pizza rolling, towards the very end, they all do a good job. However, somewhere in the middle, the person here has lots of holes. It's like a disastrous rolling of pizza dough. But at the end, they're all successful. But somewhere in the middle, as a human, we know who's actually better in doing this task. For generalization, we've also tested this on the concept of surgery. So what you see is two people doing some training in surgery, and again, people were asked to annotate which one is doing it better. In that case, experts were asked to annotate while enrolling the pizza dough or drawing, anyone could annotate. As you know much about machine learning, currently we use this huge platform called the Amazon Mechanical Turk platform to collect annotations. So you put these videos on the internet, and you give a fairly reasonable amount of funding, and people just look at it and give you their judgments. Right, so what we want is to find a function f. This is your learning now, that takes two videos, pi and pj, and ranks them based on your annotations as the outcome. The features, the function of fpi is higher than the function of fpj if that's what the annotator told you. So the annotator is saying pi is better, now you want some learning that does exactly the same using the annotations. Lots of research in computer vision and machine learning is about finding the right loss function. This is called the margin loss. So we're going through all our paired data points, and for each one of them, we are finding the max of 0, 1 minus the higher plus the lower loss. This is the same technique as ranking. This is the margin loss that is used for all ranking problems. We're not doing classification, and thus we're not doing softmax cross ranking. Okay, so this is the architecture. Well, as input during training, you have two videos. One is ranked higher than the other. And you use what we call a CNEs network. So I told you about tying weights in CNN. This is more complex. These are two different CNNs where weights are completely tied, so they share the weights. So I want the same set of weights for the first and for the second, but I want the output to be higher for the video that was annotated by the person higher. So you have to keep two pairs of CNNs in the memory. You have to forward pass, find the outcome, and back propagate where the weights between the two networks are tied or shared.
And we're using the same architecture for both?
The same architecture and the same set of weights. Formally, these are known as the Siamese networks. Interestingly, you take the concept, you're doing a ranking problem, you find the right loss, you build your CNEs architecture. In this case, we combine both appearance information and motion information. We call these temporal networks because what you feed into them are optical flow calculations of the motion. For certain tasks like drawing, the motion might be informative rather than only the image. For other tasks, it might be the image. And we wanted the system to automatically figure out which of the two types of features is more relevant, and thus we have a spatial network as well as a temporal network.
What's the difference between shared and stacked?
Stacked.
Yeah.
There is no similarity. Stacked means you have multiple networks, one after the other. Shared means they are exactly the same set of weights. but they take different inputs. That like the concept of the CNN, that shared weights. When we did this third approach, the accuracy was really good, both in training and in testing. However, when we tried to observe or understand what the network had learned something really picky at times. Sometimes the size of the hand was an indication of whether they're good or not. So it was really picking something that was not human relevant. To force the network to refine its decision to be human relevant, we added a different set of weights and losses. These are videos that humans believed are similar in skill. Right? So there are two people saying, oh, I don't know, they're both equally good. We fed the network again with those videos for which skill could not be differentiated. And we added an additional ROS where we wanted the network to also not distinguish between these. That added the invariance we wanted. We wanted the network to focus on skill. And so we fed these additional videos where there are different people without any discriminative skill. That additional pairwise similarity ranking really improved not only the results in terms of accuracy, but importantly in our ability to interpret or explain what we believe the network is learning is skill relevant. So it's not only the accuracy that was better, the visualization of what the network believes is the source of the higher skill significantly improves. This was the paper published in CDPR, which is our main conference last year. I'm kind of taking you all the way to the latest area of research, but I'm hoping that we're bridging the gap. Right, so you try the first thing, you try the base, you have a different problem, you realize there's something missing, you think what you can do, you improve it. That's your first baseline. We tested this on 4 tasks: surgery, rolling the pizza dough. These were datasets that have been collected by other people for different tasks, not for skill, and also drawing and using the chopsticks. We realized that in the lab, we had really people with different levels of skill, where people from the Far East were experts, like they pick these beans with fast pace, and people who have absolutely no clue. So that gave us this new set of results which we released as a dataset which we call effect skill. This was collected in one location, the same task, the same beans, and we just asked them to kind of complete over. We wanted the variety because, again, in the chopstick and in the pizza, at the end, they all succeed in doing the task. But somewhere through the process, they're differing in the way they're doing it, and there is a different skill. While in surgery and drawing, towards the very end, you really know. You look at the final image and you might know whether someone is better. So in this case, you see for the different tasks, you see the effect of the 2 training functions you use. The spatial training, which is the images, and the temporal training, which is the motion. And for things like drawing, spatial was sufficient, temporal didn't matter, while for things like chopsticks, adding the temporal knowledge improved the results. So this was a combined loss function that looks at the images as well as the motion. But importantly, it was our ability to look at what the network had learned. And we usually do that by feeding the output, back propagating into the network, and visualizing which bits in the image contributed most to your final decision. I believe in today's lab you'll be able to do some of these that are referred to as visualizations or saliency maps. They're really going back to the input to figuring which part of the input contributed most to your final decision. And in the case of rolling the pizza dough, it was exciting that after all our additions, the network was automatically picking the holes in the pizza as the most discriminative part to deciding skill. We didn't tell it that holes were relevant, right? This was the outcome of your learning. Similarly, in the case of surgery, it was picking loose stitches and needle passes. In the case of drawing, when the person was really good, so on the high skill, it was picking individual features. When the person was bad, saying, all of this is rubbish, anything here is significant to know the person isn't a good drawer. And similarly, for using chopsticks, it was focusing on the hand positions. These are our interpretations of the visualizations. However, these are neither necessary nor used in the network to learn the function. all rankings with human annotators. However, the human annotators did rank that the highest and this one the lowest. And you can see these examples on the project's webpage for different types of tasks, including using the chopsticks and the pizza roller. This year, I've just come from Long Beach where we're presenting the follow-up, where we went into YouTube and we said, okay, we've tried this in the lab. Can we now to go to YouTube and re-rank YouTube videos of the same task, collected by different people in different environments of common tasks? So this is, in this case, looking at applying eyeliner and ranking a collection of YouTube videos from the best to the worst. In this case, the YouTube videos were significantly longer than the videos we've tried before. Applying eyeliners is like 4 minutes or something. We've tested people tying the tie. Again, they were much longer videos, to which our initial baseline proved inaccurate. Because it was again assuming that any bit in the video is equally important to making a decision. Again, you see the same type of annotations. So we asked human annotators to feed for the same video, in this case braiding hair, which one is higher ranked. We're still in supervised learning. We're using a slightly different architecture that's recent called i3D, inflated 3D, to which we apply throughout the video. Typically, you can sum the decision across the whole videos and do the pairwise ranking. This is very similar to the last year's paper. What we did here is to add an attention module. An attention module in time is purely some weighting of different parts of the video that says learn a different weighting function than uniform. There are parts in the video that are more informative than other parts. Again, when we added attention modules, this wasn't yet working very well, because there are lots of errors that people do that are not common to all videos. They're only common to the weaker videos, the bottom of your rank. When you try to learn shared weights, shared temporal weights, they don't get picked up. And you do that by the boring task of looking at the outcome and realizing why this is not working. So in this paper, we used 2 different attention modules which specialize to become rank aware. That means one of them is focusing on high skill, the other is focusing on low skill. One is focusing on weights that represent things that are really good, and the other, completely different, is tuned by the loss function to focus on errors and mistakes. Yes?
And they are trained in adversarial?
They are trained, not adversarial. They're trained by this rank aware to say, make the first one on the first video and the second one on the second video higher than uniform. It's not adversarial. And interestingly, you look at the outcome and you see that it is really picking mistakes in low skill, and it is picking correct things in high skill, and it is task dependent. For example, hesitation in drawing, so stopping and thinking in drawing, is evidence of high skill, while stopping and thinking in rolling the pizza dough is evidence of low skill. You really don't know what to do. And that's one of the strengths of deep learning, is that you're getting out of the system and understanding that you might not have even thought of to handcraft. The metric to decide which method is better is also pairwise ranking, as I give 2 videos and I check whether the order is correct for lots of paired videos. So this is your accuracy. And again, we're kind of comparing to our previous work and showing that we're improving results for both the old dataset and this YouTube skill dataset. If that's of interest, you can look at the project's webpage. Hazel, the student who's leading this as part of her PhD, is a really good student, and we're now looking into bigger tasks that might not be short videos, even longer than the minutes long. So this is skill determination. Any questions? I'm going to give you these, again, very quick ideas that emerge from the concept of CNNs on fine-grained object interaction understanding, and skill was the first one. The second one we call action completion. Again, another student doing a project on whether the action has been successfully completed. And I usually start this by a bit of video from the Ellen show. This is a well-known US show, where the audience are shown a clip, and they were asked to highlight whether they believe the person is going to succeed or the person is going to fail. It's a comedy show, so they actually kind of, oh, okay, it's playing already. They actually show people the video, they kind of highlight, and they show them the outcome, and people kind of say, I knew that this person is going to succeed, or I knew that this person is going to fail. From a computer vision perspective, there is very little even consideration of the concept of incompletion. Right? So you look at the video, and you say, I look at someone pulling the drawer, and then I look at another person who tried to pull the drawer was locked, they haven't really completed the action. If you put that into a typical classifier, the classifier will confidently say, this is a pulling action. It's not even going to consider the aspects of the goal being incomplete, because our networks are not trained for that and are not even designed to consider the goal not being achieved. And if we start from the initial video I showed you on the people breaking the plates, if we want to be of any help to humans, we have to focus on their goals and whether they were achieved. So to do this process, we had to collect a data set. This was really fun to collect because we gave people tasks they could not complete. So we gave them plugs that don't fit or jars that are glued, they can't open it. We did tell them that they are likely to fail, so they don't hurt themselves, but they didn't know per iteration whether they could succeed or fail. That allows us to collect complete and incomplete sequences to try to even build an initial model. We also tried this on YouTube datasets. So there are lots of things out there in YouTube that are incomplete, like people trying to blow candles, and they keep blowing these candles indefinitely until towards the end of the video they really can't put the candle on. And what you see here is an example of what we call pre-completion, and that the color will change when the goal has been achieved. The bottom is the human labeled ground truth of the moment of completion compared to different methods, to which I'll tell you what method we're proposing, which is the last one. So this is pre-completion, and then a certain moment, all the candles will be blown, that's completed, as well as cases where all through the video, the little girl is just trying to blow the candles, and the candles are coming again and again. Right. Deep breath, this is a different architecture, but it's a convolutional network followed by a recurrent network. And tomorrow you're going to read about recurrent networks. You're going to hear about recurrent networks in details. But this is not only observing the current observation, but also information about the past and feeding information to the future. Importantly, the concept of this work is a belief that each frame in the sequence has an opinion of whether the goal is likely to be completed or not. Similar to what the Ellen show was doing with humans, asking them, do you believe this thing will be completed or not? And you gather that confidence throughout the sequence. So if the current frame believes it is post-completion, it's going to say somewhere in the past the action has been completed. If the current frame believes completion isn't there, then it's saying somewhere in the future it's likely to be completed. You can be more forceful and ask individual frames to decide their distance to the completion moment, whether in the past or in the future. In this work, we use this regression framework and we accumulated evidence from all the frames in the sequence. And I'll just go through the results. This is some sports where, again, ground truth compared to the proposed method, the moment of completion is being detected. And similarly, for people clearing the pole vault, where clearing it without letting it fall is success. Interestingly, we do this on normal tasks, like drinking, where you can detect the moment at which you believe the person has actually drunk, or the moment the person has picked something from the floor. Failure cases are also fun to watch, where the system believes the person did not move the glass far enough for things to be detected, because actually looking at the straw is very difficult to see. So this is a work called action completion. Both the first and the second works are still very supervised, that is still very early stages, and they're intended to figure out which out of the bunch of people the right person to learn from. Any questions? Yes. It's not huge. Here you don't have lots of data, but you only generalize the task itself. So I think in data completion we have something around 100 videos. So it's not huge. But you really can't generalize from drinking to feeding. You're only learning within the task. If you want to generalize, you need lots of data. Yes?
What's the equation behind the voting at sampling?
The intuition behind the voting is the presence of cases where there are no completion moments. As in, we're not selecting the frame at which the completion happens. Sometimes you don't even have that frame. Right? So how do you, it's not even a localization task. So you can't say, I am looking for one of those frames. It might not even exist. Right? I might finish the video and the completion has not happened. You could do it as two steps, complete versus incomplete, and within the complete, which one? But one, that is usually, you're not really learning end-to-end, you're learning two things. Plus, with this method, you can do this online. So you can keep collecting evidence to where it's getting to the stage where you can do online prediction of completion.
Dima,
Yes.
you said that you used 100 video to train this network.
Yes.
Did you use a pre-trained network? Because
Yes.
100 video
Sure.
to be a small number.
We used a pre-trained network on a large dataset called kinetics, which is focused on motion, on video. Anything to do with video, you need a large video. I think we used either UCF as pre-training or kinetics as pre-training, for sure. You needed features that are relevant for action. Yes?
Do you train a separate model per task?
Yes.
If so, do you see a path to train a single model for multiple tasks?
We tried. It's very, very hard. It's the reason we collected the data set. In both cases, in the skill and in the action, we really collected very varied sets of tasks. So they were by design very far from one another. And transfer between them really was very poor. Maybe if we had collected things that are very comparable, we could have done more transfer learning. But this was seeing the variety of tasks to this it can apply. Even between sports, we hope there is something that's comparable, but that was not the case. Right. So I told you about skill. We're moving into next part of this data set, and we're talking about videos and time, and when does the action start, and when does the action finish. And if you remember, I showed you all the effort that people had done in object detection to label bounding boxes. In video, we're still in that period of time, where we're still labeling start and end times of actions. Start and end times of actions is a very complex thing. If I say I'm putting this down, what was the start of the action? When I put it in my hand, when I started the motion, as soon as, what is the start and what's the end? The concept is ill-defined. And thus data sets which provide annotations for start and end time of actions in a video, they usually have this problem where people disagree on what the start and the end is. And in this work, we just wanted to question whether that's a problem. How robust are our current models to these hand-defined start and end times? So what we modified is just the test segment. So we trained our model typical way, and then in testing, we just moved the videos slightly by adding or removing frames. And what you'll see is in green, this is the correct task. And then we're changing just 2 seconds of time, 0.2 seconds of time, and the class is, you're going to a different class. So this is what we call adversarial attach, right? So you just change the videos a little bit. This is only just changing the start and end time. And you see that the network is crazily jumping to different classes. So in the recent work, again, we presented this in CVPR, we wanted to avoid start and end times and to use single points around the action and to see whether that's enough to learn a strong classifier. So what we're having is just one point that the person said, around here, I believe the action happened. Around here, I believe the action happened, and I have a long untrimmed video. And the model starts by saying, oh, maybe around here, and then over iterations, it's refining the position until it reaches in the training videos to the location, the correct location and extent of the action. So this is still videos without accurate start and end times. So what you see is the thick line is the ground truth, which we don't use. And what you see are these models being refined over time to get closer and closer to the ground truth. And interestingly, you see the long video of pulling a drawer refined into the moment of pulling by looking at lots of examples from lots of videos and finding the discriminative part without being biased by these start and end times. I'm not saying more about this, but just in case you're interested. We also have lots of work on using LSTMs or RNNs in video, but because that's the topic for tomorrow, but if you're interested, look at our latest paper called Dual Domain LSTMs. Okay. Videos tend to be associated by other types of data. Typically, they are associated by audio, right? So we have more than one sensor, not only video. So we've done some work on audio and video. However, before we do that, I'll tell you about our problem with language when it comes to video understanding. For example, you've seen lots of works on object detection, and you see an image and say, this is a dog, this is a cat, this is a car, this is a tree. And in actions, we try to replicate the concept. So if you think of an action that is open, think of an open action. It might be something like this. That's an open action. Very good. I can build a classifier of things that are open and things that are not open. And the objective is to find this decision boundary of what's open and what is not open. Then I learn a different class. Let's say, what name would you give this one? Slice, cut? Yeah. Let's say cut. Very good. I collect a few examples, and I can now differentiate between open and cut. And then life becomes complex. The problem with overlapping is our inability at the moment to learn very good multi-label classifiers. We're really good in doing this. Architecture is done really well. We're not as good in doing this. And you can make things even worse as you increase the number of classes and as you increase the overlaps. Right. So typically, a single verb might be very confusing to decide the action. And the solution in computer vision at the moment is to select labels that are non-overlapping. So you have a data set and your labels are run, walk, open, close, no risk. I can't learn cuts here. Problem. The second solution is to learn labels that associate the verb with the noun. So to learn open drawer, open bottle, open fridge, and every object new in the world, I need another class. Scalability is tricky, collecting data is impossible, and you can't really open anything else you haven't learned. So it's really constraining actions to non-classes. Mike, who's the student leading on this work, has been working on a concept of using multiple verbs to define the action. So in that case, if I say open, hold, and pull, I am constraining the set of pulls to things like open cupboard or open fridge, and I'm getting rid of things like, I don't know, open bottle by twisting. So I'm using multiple verbs to better describe the interaction. Of course, how many verbs would you do? How would you label this? So in this case, we started by asking people to annotate videos by multiple verbs. Do you think that verb applies? And people would say, I think this is pouring, I agree, it's also filling a cup, you're moving, you're still grasping, it's not open or closed. So you get a consensus of people's decisions. The annotators agree when the verb is relevant, they agree when the verb is irrelevant, and they are confused when the verb is relevant, but not really fully describing the action. After we've corrected the details, okay, how can we learn this ambiguity? How can we feed this ambiguity into the learning? Typical solutions is we call it majority voting. I ask people and I take make the decision they like the most. There is also work on multiple labels. I find the threshold, and if something is above the threshold, it's a valid label. If it's below the threshold, it's an invalid label. Mike really wanted to model the ambiguity as is. So to regress into this decision with its ambiguity. This really allowed us to do very smart retrieval tricks. So on the top, you see querying the videos using something that's opened by rotating and something that's opened by pressing. And these are the top retrievals. So all the top ones are things that are opened by rotating between the tap and the burner. All the bottom ones are things that are opened by pressing. Interestingly, open tap ended up in different places depending on how that tap is opened. So this is an even finer grain than using verb nouns. And similarly, you can query things like rotating, which none of them are rotating by default, but they all have some element of rotating, because you have this embedding space. And similarly, you can learn something like what holding means without any of these actions being hold alone. That some element of holding on something as part of the action. You can look at multiple datasets and see things that are done similarly. So you can see examples of someone, do I have this? Yeah, of someone pulling a drawer of printer or putting a drawer in a freezer, right? And both of them are being retrieved by this multi-verb representation as comparable. Also recently, work currently under review is looking at this in a more embedding system with longer videos. So you have something like I am putting meat on a ball of dough, and you have the relevant video. So trying to link these, we do this by looking at the caption, then by separating the verbs from the nouns. We're building what we call an embedding function. That means in this space, we want the verb to be close to that action, and the verb and the nouns to be close to that action. So that's the verb and the nouns, and we're trying to build a space where this verb is close to that noun, that video, and those nouns are close to that video, and then we combine these to be able to retrieve labels for new actions. Embedding is increasingly becoming popular in computer vision because of the difficulty to define boundaries of separate classes. Can I skip this in the interest of any questions? So again, we do have an issue with learning labels in video. These issues are related to the labels themselves, the start and end time, but they could be labeled to other things like what's the objective? What label do I want to give as an outcome? And that's an issue maybe why people are trying to move away from supervised into unsupervised, but currently supervised methods are still doing much better. Any questions? Where are we? Have I lost half of you? Less? More? You with me? Okay. Audio. Remember that we're focusing on first-person vision, and this is the type of audio we are looking at. If I ask you what the person is doing in this video, suggestions.
Eating and preparing coffee.
Preparing coffee, some of you got the eating. Yeah, and now let's look at the audio. There is a lot of signal in the audio, a lot of signal in the accompanying audio, that assuming using only the video might be problematic. Similarly, it's not always helpful. Audio is not always helpful. Let's look at this action. So the action itself is soundless. And you have lots of sounds in the background that are not related to the action. There is the phone ringing, and there is the radio or the TV playing. So sound is helpful sometimes, but not helpful at others. Plus, there is little work in trying to integrate video with audio. So in this work, we are looking which you're seeing the action and you're hearing it might not always overlap. Let's think of you closing the cupboard. The motion happens first, it's soundless. The sound happens later, it has no motion. Trying to link these, we know that they are the same action. But the system, if the system looks at a moment in time, it's going to get either the motion or the audio or the appearance change. So we got stuck. What do we do? How do we make that decision? We want to combine these modalities, but they don't sync. They're not occurring at the same time. And always when you get stuck with how humans do something smartly, you go to psychologists. How do humans do this? And they told us there is something called the temporal binding window in humans. So we even hallucinate. We tend to link things that are not at the same moment in time, even if you move them incorrectly. Let's assume I show you something, and I play the audio not when you expect it, but even further. Humans tend to correctly link these and say it's the same action. So we're more bound to binding than to separating. We actually believe that two signals are correlated even when they are not. And there is evidence in psychology, because they do all these experiments, that the binding window is bigger in children and gets smaller in adults. So as you start, you really have this large binding window where you even accept audio and video that are completely unrelated, and slowly you learn causality, and you tend to kind of decrease the binding window, but still the binding window is bigger than reality. You still are flexible in accepting it. Lots of theories of why that's the case. The speed of light and the speed of sound are different. However, we said, great, let's take this idea and see whether our network now can benefit from a bigger temporal binding window. So what did we do? We actually said we're going to sample the modalities within a bigger temporal binding window and put them into the learner. So that is the time. This is a big temporal binding window from which we sample bit of audio, bit of motion, bit of appearance. We keep sampling. It's a typical data augmentation trick, right? So you link things. But importantly, we want the network to start to find these shifts that are most discriminative to make the action. Right. So what we're having are these windows from which we're sampling images, optical flow, and audio. We have 3 CNNs, right? 3 different CNNs, and eventually we are fusing the decision by concatenating, adding a fully connected layer, and we even have multiple temporal binding windows to model the progression of the action. This is work under review, so you're not going to find it yet out there. Let's look at more details of what we're doing. So you have the audio. You usually transform the audio into a spectrogram. A spectrogram is an image that models the frequency and the occurrence of that frequency. Once you've mapped the 1D audio into a spectrogram, great, it looks like an image. We can use a CNN, right? We don't care that it comes from a 1D. Now we deal with the spectrogram as a 2D input, and we apply the same convolutional 2D architecture that we apply to images as well as optical flow. Usually in optical flow, you need the progression of the action. We use BN inception. BN means batch normalized. It was the first architecture that introduced batch normalization. That's why its name is still BN inception. BN inception, then we do pooling, we do reshaping. So we model this into a long vector. We concatenate, we build a fully connected layer, and we also have 2 outputs, one to predict the verb and another to predict the noun, 2 separate outputs. That allows us to model more than combining them, because I learned what open is and what bottle is, and I have more examples of these than open bottle. So this was the output in verbs. This is what types of verbs were best described using which modality. So you see verbs like eating or spraying to be best described by audio. You see verbs like throwing to be described by RGB, and things like dividing or mixing or shaking to be motion specific, and you see the overlaps. You see that lots of videos benefit from multiple modalities. And similarly for nouns, understandably for nouns, motion isn't a good discriminator. It's not the motion of the object that tells you what it is. It's usually its appearance as well as its audio. It was really nice to find things like the extractor fan in the kitchen to come immediately under audio as the most discriminative things. I'm going to tell you about the data set on which we're evaluating this. So this is the applications data set, but you can see how we're evaluating the top one verb, noun, action on 3 modalities, as well as combining 2 modalities and all of them. It's nice to see that we are really benefiting from adding all these modalities using this temporal binding window. Importantly, audio in egocentric vision, so in wearable vision, is far more successful than audio in third-person vision. So if I put the camera here and I observe a far action, the audio is really going to be far. But when I carry my camera and move around, the audio is going to be there as I perform the action. So we're reintroducing the benefit of audio by using the egocentric domain. Right, so this is where we say we're better than everything else. But this is very much ongoing work. Next, I'll tell you after we've decided that we're going to start working on first-person video and object interactions, it was time to collect a large data set that people can now evaluate object interactions on. And Epic Kitchens was this data set we've collected in Bristol. So it's being led by Bristol, but we have collaborated from the University of Toronto and the University of Catania in Italy. And this is the team of people who've collected Epic Kitchens, which was released last year in ECCB. First, if you want to collect data, focus on the scale. So what you see at the bottom are what we call third-person videos. So these are cameras looking at people doing actions. The middle are previous data sets that are trying to collect data from wearable cameras. And at the top you see Epic Kitchens. And by far, we have scaled egocentric vision significantly. So we're talking about 40,000 actions and about 500,000 bounding boxes from 32 different environments. We're very proud of the way we collected the data set, which I'll tell you more about. So Epic Kitchen started with a data collection where we gave people wearable cameras, in this case GoPros, that they can mount on their heads. We asked them to take it to their homes. The difference in collecting between, let's say, a university kitchen and your home is that when it is your home, you're going to do things very differently. In your home, you're going to open the cupboard while you're filling the kettle, while you're doing a million other things, and that's where the knowledge of interaction is going to fundamentally change. So we asked people to collect everything they've done in their kitchen for 3 days, only the kitchen. From the moment they prepare the coffee in the morning until the moment they wash the dishes in the evening. After that, we needed some labels. So people were asked to watch their videos and tell us the story of what they were doing. Oh, I was getting milk, I was preparing coffee, I was opening the tap. These were live narrations from which we created action segments, object bounding boxes, and released the challenge. And I'll take you through the process. So this is the type of footage we've collected. It's 60 frames per second because motion is very important in actions at full HD. And we ask people to start recording once they get into the kitchen, stop recording once they go out. And we've collected this in 32 kitchens, each person for 3 full days in 4 different cities. And you can see even the times at which they've been to the kitchen, which we released as part of the data set we collected between May and November 2017, resulting in 55 hours. After the collection, we asked them to talk over the videos. That talking gave us this timeline in the video, along with a sentence of what they believe they had done. When we started collecting this, because we were collecting this in English-speaking universities mostly, I thought everybody could annotate in English. However, we had the person who is, for example, had been in England for 10 years. Once you ask them what's the name of this tool in the kitchen, they have no clue. They only know it in the native language. They don't know it in English. There is no need to know it in English, even if you work in England for 15 years. And so we shifted. We said, okay, just whatever your language is. So we collected in Italian and Greek and Chinese and English and Spanish. From these narrations, we went and refined the start and end times of actions so that we can train models. I told you before, I hate start and end times, that's true, but still the models currently still expect start and end times to be strong models. And that gave us something like this. Now we have labels with every step, and they could be even concurrent labels. And these are hours of footage where we're capturing all the interactions and we're giving them labels. And you have things like emptying your bin, peeling potato, putting your contents in the Tupperware, pouring milk, etc. From those labels, we found the verbs and the nouns, the main verb and the main noun of each action. Focusing on the main object or the main noun in the action, we went and extended the time and collected bounding boxes at 2 frames per second, to which you get these active object bounding boxes. One of the hardest tasks was to come up with a meaningful output of all these things that people had said. Someone said take, someone said grab, someone said fetch, someone said pick up. To us, it's the same action. And lots of the effort that was done to group these into, let's say, a common class was done manually. There was nothing out there in language to group these. We could not find any corpora or any natural language concept that did meaningful grouping. You can't do, so WordNet is based on co-occurrences of words in, say, Wikipedia or in written text. So if I give WordNet something like take, open, and another word like close, and a word that's like turn on, the distance between open and close is far smaller than open and turn on, because in the same text, you don't find open and turn on co-occurring, but you find open and close co-occurring. Co-occurrences in written text have nothing to do with object interactions because we don't write these sentences. There is nothing in written text that says open fridge, pick up milk. That's not written. And accordingly, current corpora are useless for our task. You can read in the paper all details. We tried WordNet and glob and everything you can think about. And eventually we had to do most of it manually. Similarly, we group nouns. We group mozzarella and parmesan and all these things into a cheese category. And even after all this grouping, we have 125 verb classes and 331 noun classes, that's beyond grouping. And we have what is real life, a hugely imbalanced data set. The y-axis is log scale, right? So you have 10 times more opens and closes than pours or drying or turning. So you have a huge long-tail distribution. Typical attempts to collect data sets tend to be balanced, but that is active. Right? I want to collect 100 examples of drying and 100 examples of open. If I look at one's kitchen, they can never be balanced. And if we don't address the imbalance in reality or in life, we will not be able to solve for typical action understanding. And these are the 331 noun classes grouped into this understanding of what to do in the kitchen, starting with vegetables and fruits, and using kitchenwares and appliances and some furniture, etc. These are in actions, and these are in the bounding boxes. It was very interesting to figure out the top most popular vegetable in our kitchens. Any suggestions? No? No? So, onions, regardless of the cuisine, whether it is from China all the way to Canada, all the cuisines start by cutting an onion. Next, you have to think about your objective and what type of training testing splits do you want the data to have. And that's why we had 2 test splits. One, we called it the scene test split, where for 28 of our kitchens, you've seen some sequences in training, and you left some sequences out for testing, but for 4 other kitchens, they were completely unseen. Can our models actually generalize to new or novel environments. So these are the statistics of the data set, the size of the data set, the narrated segments, the action segments. And to avoid overfitting, we kept the test annotations beyond an evaluation server. So no one can see them, they can just submit the results and get the overall findings. And this is what we released. Full HD with audio, as well as downscaled RGB and optical flow frames, so that people can download the low resolution and train their models. I always like looking at how clear the footage is, and how obvious it is what the person is doing. We released 3 challenges. 1 is what's the object, 2, what's the action, 3, can you anticipate the action that's going to happen in 1 second? That potentially is, if you want to give guidance, you have to know a little bit of what the person is doing next. So in September last year, we released the leaderboards on a platform called CodaLab. So that means people can submit their results. They have the training set, they can build the models. They submit their results, and they can evaluate the performance and know where they are relative to the leaderboard. And 2 weeks ago, 1 week ago, we released the first set of results. So the first set of winners of the action recognition challenge. So that is, given a start and end time, can you predict the verb and the noun as well as the combination? So the complexity of the data set, the untrimmed video, we just simplified it saying, let's start with trimmed videos. Can you figure out what the action is? 25 teams competed. We had about 230 submissions. And this was the final leaderboard, where people, interestingly, had very similar ranking between the seen kitchens and the unseen kitchens. That's good news. That means if we solve a problem, we can generalize to new environments. That was, to me, unexpected, that really models were very comparable. And these were the first set of winners, and now we're going to open the leaderboard again so that new people try it, and we get a new set of winners for next year. This was just 1 week ago, members of the team as well as the set of winners. If you're interested, look into Epic Kitchens. You can download the data set. You can look at what people are producing in terms of results, or the main paper of how we collected the data. I always say that being in machine learning or computer vision, you always have to collect 1 data set in your lifetime. That's like a priceless learning experience. You're in a better position if you collect it in a team, like less painful, less boring, but you really have to understand what data set collection is about. If you only download data sets with their labels or train models, you have a very weak understanding of biases in the data, errors in the label, problems that don't relate to other data sets, and that's a priceless learning experience. Any questions on Epic Kitchens before I move to the last part? Yes? Right. Can we define an embedding that relates things that's suitable for the kitchen? What objective would that be? That's probably the main question. Because you can define an embedding that relates the video to, let's say, the video in 1 second. You can say, I want these to be as close as one another. And then you find an embedding that is sequence related. You can define an embedding that relates the video to the verbs, or the video to the nouns. It's really, the problem with embeddings is that it really very much depends on what we call your pairs. Usually you have an anchor, a positive pair, and a negative pair. And you want the positive pair to be closer to the anchor than a negative pair. And then you do lots of tricks like hard mining. You define a better embedding with time. But it is really defining those that is not trivial. Because usually you want a multi-dimensional embedding. You want it to be related to the object and to the noun, and to the verb, and to other actions, and to future actions. You really want, and there is no way to define triplets like this as yet. That's why the work you've seen at the very beginning, where I show you the verb and the noun embedding, this was done on Epic. But again, the objective was eventually action recognition or action retrieval. I retrieve similar action. Yes?
Is there any interest in classifying for the specific nouns, not the class? Like, are you...
The object detection.
Yeah, like detecting walk specifically, not plan.
Detecting?
Like, you showed an example with
in very different ways. I wouldn't say exactly the one you're saying. There is interest in tracking and looking at the state change of the object, so the object before it's cut and the object after it's cut. So there are interests beyond what we've defined, and that's why the data collection was beyond, let's say, the challenges, which is why we like the way we revised. Yes. Meaningful, yeah. Yes. Okay. So I think there are two aspects to the question. The question was, you went for very unstructured data and you tried to structure it, and that's why you needed lots of annotations to do that. Why didn't you look for a way to have the structure maybe more controlled? Previous attempts to collect egocentric vision tends to give people instructions. So to collect something that's more controlled, I give you a recipe and I say go and do it. There is stuff that says one called breakfast, one called 50 salad, where I give you the steps and you replicate it. That gives you lots of structure and decreases the amount of annotation. If you look at these videos, they look like a robot has been doing this. Because once I tell you what to do, you're going to follow that order in a very unnatural way, right? You're going to open the fridge, pick up the milk, open the milk, because I'm following the steps. I'm really acting like a robot. If eventually you want to give guidance to people in their homes, we're very far. As in the features we collected and the models we built are useless. So it depends. If your objective is really going into people's natural environments and helping them, you really have to collect from people's natural environments. We were also part of datasets that were collected with these instructions. They're far more structured to collect. But that gives us a very weak understanding of our final objective. So wearable cameras, the belief is currently everyone has their phone. You see people in the street looking at their phone and walking through. Once you give them this wearable solution, people will adopt it. Our problem with wearable computing is currently hardware. We don't yet have the wearable phone. We have the handheld phone. We don't have a good wearable phone. But you can imagine people now hoping for the time where they can actually be hands-free and still stay connected because we're addicted. And thus the objective is to think about that time when we will all have this wearable computer in our native environments, and if we don't start by preparing those models that can actually learn from people in natural environments, we won't be there. That probably was one of the objectives. The other objective was really to collect the imbalance. All the models we build, all the models almost everyone builds, assumes that the number of examples of each class is the same. And the more we do that, the further we're going to be from reality. Nothing in the world is balanced. Biases are like all through. So in this work, we've done some hierarchical analysis of classes, so bigger classes and smaller classes. Distinguish first vegetables from fruits, and then going fine grain, because that does help the balance a little bit. But machine learning people, we're now in a bunch of machine learning people, they really don't like to look at imbalance in the data. They consider it as something on top of their solution. If it's worth imbalance, it's fine, we'll solve the imbalance somewhere else. And I think practically, that's a big problem. That's a very, very big problem. As the longer we build models that assume balance, the further we will be from applying them and using them. So probably we're really wanting to hit that. Yes?
Sorry, I want to come back just to the example that when you talk about the computational similarity between the two terms, open and temporal.
Yep.
I guess there is some suggestion about coordinate,
yeah.
but there is some more specific tools,
corporal,
like OpenNLP. It's gonna give us great similarity between these two terms.
From which corporal? But the semantics, okay. Right, because we've done lots of work on this, I'm identify what the problem is. The problem is semantic similarity is learned from written text. It's learned from something that had been written. What do we typically write? We write novels, we write essays, we write Wikipedia pages, we write how-to. This is what written text is about. Nothing in the written text, even in dictionaries, correctly relates the actions we're talking about, the semantic similarity. So the semantic similarity between open and turn on is very contextual, right? It's very contextual with the video. It's not always. Open and turn on are not related in many cases, right? But they are related when you look at the context. And that's where current corpora or NLP alone really fails us. If there was something written, for example, when you look at a kid trying to open a door, you tell them, oh, you open this by holding it, turning it, and then pushing it. You give them that set of instructions. That set of instructions is not written anywhere in written text. So for us, or for anyone doing robotics who hopes to use NLP for anything, because that is not written text, it's just spoken, we don't have either OpenNLP nor GLOB nor Word2Vec to give us the semantic similarity we're hoping for. If you have a solution, you're very welcome to help us, because we're doing this manually. But yeah, we haven't found anything out there that can give the semantic similarities we're hoping for. Speech? Yes? Because we don't, okay, for Word2Vec to learn from our similarities, we need to have defined the similarities manually anyways. Because for Word2Vec to define the similarities, it really needs to learn these co-occurrences. We don't yet have these co-occurrences written in large quantities to learn a corpora. In our case, we didn't have open and turn on rewritten. We had only open, and we have turn on somewhere else, and we needed external knowledge to link them. We don't have them. It would be nice if someone writes them. Yeah. Right. Movies are very interesting things, and people have tried movies. Interestingly, movies are talking heads. In movies, you're going to find 4 actions: drinking coffee, smoking, sitting down, opening car doors, and walking. And that's it. You don't find opening cupboards. You don't find real cooking, right? Movies tend to tell the story by cutting what we call boring actions and keeping a storyline. And that's why there's a deficit called Hollywood 2, which really learns very well coffee drinking and smoking. But it doesn't learn anything beyond. We wish if movie people would film more realistic movies we can learn from, that would be great. But currently, apparently that's boring for humans to capture. Broken films, apparently, that's the new Yeah. Right. Sharing more about the experiences for the data collection where we started from. Do not rush into collecting data. Take your time, sit around long meetings, figure out what the difficulties are, divide the tasks, appreciate the time it's going to take to do the tasks. Plan really well. Collect your first small subset, test it is what you want, because usually it is not. Usually the way you annotate it, if you go and collect 1,000 images in one go, that's usually not very helpful. Collect 10, you're going to throw them in the bin. These are not going to be useful. Collect 10, annotate them, figure out the ambiguity annotations, the time it's going to take, the cost it's going to take, right? And then figure out, okay, can I optimize it better? Have a team that believes in the problem. That's really, really important. And if you can't find it, go and talk to people in other universities who might be interested. So for example, if at Bristol alone we didn't have Catania and Toronto, it would have been really hard. Group, because lots of people are interested in big data sets. Find your group and but you still need someone to lead the team, right? But find a group of people who want to collect, but spend months discussing and figuring out how you want to collect it. And don't worry about throwing away your first batch. Show people the potential once the dataset has been collected, right? So we have people who are doing skill, people who are doing language, and all of them were short of datasets. So bringing them together and say, look, if this dataset is collected like this, you will be able to do your project. So group people who will benefit all from the dataset. Don't collect the dataset very quickly, right? So I told you we started in 2014. In 2018, we collected this dataset, right? So don't rush into data collection. Start small, figure out what the problems are, figure out what you want, and then when you have a clear plan, press the pedal and go and collect, and be confident and prepare it for release. Talk to the researchers about what they want in it. Yeah, probably these are the do's and don'ts. Yes. We currently train on balanced datasets, that's true. Currently, we don't even do that. Currently, we train on balanced and test on balanced, not in EPIC in general. In EPIC, we're training on biased, so imbalanced, and we're also testing on imbalanced. We're not balancing the training like it. We can't. Yeah, but then you end up with really small samples. Because you have only 100 examples of dry, but 20,000 examples of open. You're going to throw the 20,000 to keep 200 to train on balance. Yeah. Wearable cameras. So as I told you, we specialize in wearable cameras. And we believe wearable cameras are coming. And we want to prepare useful methods and models to help you deal with the world once the technology is there. And I always ask questions. Warning sign, privacy. Do I want to wear a camera? I do not want to wear a camera. Big brother, all these privacy concerns. And I'll share with you my thoughts, and I would very much like to hear yours. Why are we really sensitive to cameras? We seem to be very happy to sacrifice lots of privacy things. Our phones are tracking us everywhere. How many of you have turned off the GPS? Ooh, you were really very privacy concerns, right? You turn it on only when you want to know the directions. At least most people are not collecting your data if you turn it on. Some are. But at least Google is.
But your
telecom company knows where you are in cases. Yeah, that's true. But at least you try. We seem to be very happy to tell Facebook what we like and what we don't like. All the time we're saying like, don't like, don't like. Note that your likes and dislikes are probably the most private thing, because I can look at you and I will never know your likes and dislikes. I still know how you look. Your look is your public image. But your likes and dislikes on a particular concern or political opinions or social, this is something we're happy to hear. We write all these long things on Facebook, our thoughts and our opinions, and that seems to be okay. All our texts on WhatsApp and messages, this is being tracked. But the moment we say cameras, panic. And for someone in computer vision, that drives me crazy. I'm like, what do you mean? But how you look is something you go to the street and people see you. This is a public image. It's not your private image. Your private image are your thoughts. Your public image is how you look. Why are we so concerned? And I'll give you an example. 2 years ago, we had this farewell party to one of our colleagues. And I had this colleague of ours that was just taking pictures throughout. He had this camera, he was going around taking pictures. These are my pictures after that party. So it's me, 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 me. What do you think I did with those pictures? I chucked all those in the bin. This is all me, right? I didn't like how I looked here. I did not like how I looked here. I was not too happy. stand in front of the mirror. We look at how we look in the morning in this serene, calm face. We're not eating, we're not talking, we're not laughing. That's how we believe we look. And when someone takes an image of us we're eating or talking, like, it's not a nice image. And your family, your loved ones say, this is a good image. No, this is a bad image. Because we really don't see ourselves. We have this biased view of how we look. Standing in front of the mirror, this nice smile, that's how we think we look. Otherwise, we don't see ourselves. Worse, photography is all about this perfect shot. The right angle, the right view. These are the photos that get published and get focused. We really don't see ourselves. We do see where we are, we do see what we're doing, we do see how well we're doing it. We have an egocentric view of the world, but we don't really have a view of ourselves. We are very reluctant to really know how we look. I believe that our sensitivity to cameras is not related to how private they are. They're very much related to the concept of a perfect photo. And that's why when you see a camera out there, you're like, oh, but your likes and dislikes on Facebook don't seem that private to you. If you disagree, let me know. I would very much like to know why people think cameras are the scary factor they are. Being in computer vision is very frustrating because people have these Alexas at home that are listening to every word they're saying. But if you tell them put a camera, that's where the panic starts. Again, lots of credit goes to all the team. Please join me in appreciating all of their efforts. Most of them are doing this work as part of their PhD and postdocs, but they are really building a very strong group to which I presented some of that work. And I'm getting probably faster to the end. If you have any questions, let us know. If you are interested in any way in egocentric vision, there is a mailing list that we have at Bristol to which you contribute all data sets that are in first-person vision, all publications, journal, etc. that are in first-person vision. We're very specialized, but I hope that I showed you that what we're doing is of potential benefit beyond first-person vision, but of prime relevance to applications. Yes? Skill. Identify the skill of people. Right. In deciding people's hiring. So remember that computer vision is replacing human cognition, right? So a human can look at how you do things and make a decision on your skill. We're trying to replicate this by an automated system, right? So already humans can look at how you do something and hire you based on your skill. Now this is computers wondering whether they can do the same. Hopefully, we will not be in a position where computers hire us. That would be a bit scary. We still want to use them rather than get used by them. But I think you all are in the forefront of deciding whether it's computers or humans who will be the winning factor at the very end. I don't believe in the scary aspect that computers are taking over. But yes, skill determination. Researchers tend to really like to publish their work. So if an industry wants to use skill determination, our model is out there, our data set is out there, and anyone can give it a try. Yes?
Did any of this research went into business?
No, none of that research went into that business by us. We publish, and industry can do whatever it wants with it. We get funded by the taxpayer. So our funding is from the taxes of individuals in the UK primarily, and the condition is to publish that work, not only for the UK, but internationally. And to that, regardless of any political decisions we know about things, the Western world is really publishing. The only thing that they are really relying on is that the people who will be reading it are only in Europe or only in the UK. And that's why NASSMA is a major thing, saying, the research is out there, the knowledge is out there, we just need to build a base outside for people to prepare. But we really have to publish. We can't keep any of the research we do unpublished or directly use it into business before or without publishing it. And that's a condition of all our funding. And similarly, in in many places in the US, unless it's security funding, you really have to publish. So the research is out there. As I told you, it's not written in a way that it's easy to read. We are a very elitist people in academia. We write research sometimes too mathematical, sometimes too complex. We believe that's the better way. But the research, the content is out there for people to read and use in any way or shape or form. I fully understand that the first set of slides might have been more relevant to your work. The second was very much advertising what we do, but hopefully it was showing you how we've done it and why we came to the conclusion, and that might assist in decisions you've made. And I would very much like again to thank Hussein for inviting me and say, come to talk about computer science. So big appreciation to him and the team, and thank you for listening.
So we'll have lunch now, and then we'll resume with advanced topics on optimization.